This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Welcome back after the break. It's unfortunate we have a 9 a.m. Monday lecture, day after daylight savings comes in, so it feels like 8 a.m. That's the way it is. Today we're going to spend 2 lectures actually talking about reachability analysis and model checking. So far we've seen how to construct models of systems, how to compose them together, use linear temporal logic to describe their behaviour, etc. But we haven't looked at the reliability of the systems or being able to predict exactly how the machine is going to work in terms of some sort of proposition. Okay? And that's typically how safety requirements are stated. We don't want something to happen. We have a model of the system. We want to prove that that something we don't want to happen can never happen. And that is indeed reachability analysis. Just before we start, 2 quick points as updates. The project specs again on LMS, if you haven't seen them. I will just mention, because I've answered about 10 people's emails about this, there'll be no obstacles on the ramp section, okay, of the course, right? So you could have your state machine controlling the robot in 2 distinct modes, if you like, in a ramp climbing mode or an object avoidance mode, right, safely. You don't have to combine the 2 together to avoid obstacles on a ramp. Okay, hopefully they'll get rid of some extra queries I'll get. Lastly, 3rd assignment is on LMS, and it covers things such as scheduling and stuff. So it's over the last sort of 2 to 3 weeks previously. Yeah?
Is that the last assignment or is there another one?
No. Do you want another one?
No.
Okay, cool. Yeah, AO3 is the last one. So they were roughly spaced every 4 weeks. That was the idea. Okay, and AO2, the solutions are obviously up, and the marks should be coming back to you when your demonstrators get around to marking them. Any queries, send them to me. Okay, so let's pose a problem, a problem that's simple to pose, but we're going to find very difficult to check. And we're going to have to introduce a couple of techniques of doing this. So let's take your Kabuki robot here and let's make it have to navigate some obstacles and get to a particular point. Okay, so you may have explored this already in linear temporal logic. Starting at a square, we grid up the region. We've got obstacles at fixed locations. We may know a priori where they are, we may not. We may have to react to the environment with sensors, that's all right. And we want the robot to end up over at this particular point phi here. So there's a specification of the problem. The robot must eventually reach that red square phi. And we can write that as a linear temporal logic equation, right, in terms of a proposition. We could further modify this and perhaps pick some intermediate points here along the way, right? And we can call those phi 1 up to phi n, and say the robot also has to reach those destinations as well. But we could also put a constraint on there that the robot has to reach those destinations in a specified order. Okay? So now it's starting to get a little more complicated. How can we show, given, say, a model of the system here, the robot, its algorithm for navigation, a model for the environment where these obstacles may also be not be static. They could be moving. So you could imagine like this malicious environment here where blocks can move up and down, trying to block your robot, and your robot's trying to get around them as they're moving, one square at a time. How can we formally prove that, firstly, your robot can get to the other side, but secondly, that perhaps that there are additional constraints, so that there are squares that must be visited in order? Can we actually prove that formally? Now, note, this is totally different to simulation. This is not about popping an algorithm into a simulator, CyberSim, whatever, LabVIEW, and just cranking it out and saying, yeah, got to the other side, it's all good. Because that, it gives you a little bit of comfort, but it's not a formal way of proving something, okay? It may have just worked because it just worked, right? Particularly if maybe these things can move and their movement is maybe random or non-deterministic in some way, they're modelled, that we may have, you may have just been lucky in getting over to there. You run one simulation run, you get there, it's all good. Or even worse, you run 100 simulations and 50% of the time it makes it and 50% it doesn't. And you've got no idea why it doesn't make it, okay, because you haven't done it formally. It's just failed at various points. Okay, so we're going to start off very simple. We're going to use a trivial example to work through reachability analysis, and it will seem trivial because it's such a small state space system, but believe me, things get complicated very easily. So we're just sticking with a simple example. Okay, so this is called reachability analysis, and it's in blue because it's important here. So what we're going to do is, given a system, we're going to compute the entire set of reachable states. Now, when we composed state machines previously, side composition or in Cascade and stuff like that, we could do the same sorts of thing, right? We could come up with joint states of the overall composition and work out ones that didn't have transitions coming into them, so they're unreachable. Okay, but we're going to be doing this as via a search algorithm, other than explicit composition. Right? So instead of forming some massive composite state machine, we're actually not going to do that. We're going to just take the individual state machines and kind of do a search on them. So we're going to use reachability analysis. Now, model checking is this algorithmic method. And anytime it's an algorithmic method, it means it's amenable to chucking into a computer to do a lot of number crunching and work out what's going on. But what we need is a formal specification. And we express the formal spec in LTL, right? So it's very nice. It's a very compact representation of a constraint on the system. There are two types we call safety and liveliness. Safety is the easy one. There's a state you'd never want to go into. So we specify that as a safety constraint. And we can write that as LTL. We'll do that later. Model checking is such an important part of the verification of embedded systems that the people who came up with it in the early 1980s, 3 of them got the Turing Award, which is like the Nobel Prize for computer science. So it's that important that these guys got the award for that. Okay, so reachability analysis is part of a model checking suite. Okay, so what we want to do is we want to make sure that the machine that we're looking at, the system, let's call it, either something good happens or something bad does not happen. That's kind of the two simple ways of explaining what we want to look for. Something good happens eventually, or something bad never happens. And by bad, we typically mean a particular state of the system it never gets into. So what we do is we write a property of the system that we want to check in LTL, because it's a nice compact way of representing it. And what we do is we compose not only the system, so the FSM of our description of the system, but also the environment as well. Now, we can go back a step. If we think of it this way, S would be the robot's behaviour as coded, as modelled in a state machine. And the environment would be, for instance, if these blocks were able to move, the state of the system here, where we would represent the locations of the blocks in a grid as a state of the system, and the state could change. Think of these as ones. This is a matrix here, and a 1 represents where the block is. Obviously, they can move, then the ones can move to different rows if we're just going to constrain them up and down. So that would be the environment. And the idea is that the composition of those, we're going to call that M, model of the whole system, has no inputs. That's what's represented as what's modelled as a closed system. That's important for the formal verification techniques we're going to use, that the system is fully self-contained. Okay? Everything you need to model the system is already embedded in there. Yeah? It's been composed together. Environment and system composed for our model. Now, so that's a closed system. I'll talk about that in the next slide. Then we run some formal verification process on here. And it turns out that algorithmically it's really nice to be able to do it. There's a few ways of doing it. And we come out with two obvious answers. Yes, that something's been proved, and we get a proof for that. Or no, it fails, and we get a counter example. So we can demonstrably prove, for instance, that it ends up, the machine may end up in a state eventually that we don't want it to end up in. Okay? And you can already think, when I keep saying eventually or never, right, or always, these are LTL style operators, right, G and F. Okay, so I mentioned that we look at the composed system of the system and the environment, S and E, and it's a closed system. We've been dealing with open systems usually, right? It's just some state space here, right, that's described by an FSM diagram here, and we have the types of the inputs and the outputs. A closed system simply has no inputs, right, but it can still have outputs. And for verification purposes, what we do is we combine them together, composing the system and the environment models. If we don't know enough about the environment, well, we may have to sort of engineer some stuff and dumb it down, so to speak. Okay, we can use non-determinism there for that. All right. So, what we're doing is we are going to be globally checking something. And most model checking relies on checking GP, bold GP. So P is a proposition. So it's a property on a single state. And we express that as a logic proposition, right? Not something or something, something and something. If you've got a composition with two state machines and you've got two possible states the machines can be in, you can compose them together in a proposition, right? So, for instance, anything. You could add them, or them, whatever you like. And we want to say that globally, this proposition holds in all states. It might be clearer when we look at an example, right? But we don't want something to happen. We can state that as a logical proposition, and we say that globally we don't ever want that to happen in all states. Okay. So if it's false in one state, then the GP doesn't hold. Okay, so what we have to do is essentially, you can imagine, if we're checking this proposition, we've got to check this proposition in every state of the composed machine, and if it fails once, then GP doesn't hold, and therefore our overall proposition on, our overall LTL formula on something won't hold. okay? Typically what happens is you get an English requirement. Once again, it's like a safety requirement. You cannot have this happen, and you can state it like this. But we're going to have to go through and check P for every state. So, it's what we say here simply, I'll put that in inverted commas. What we need to do is we need to enumerate all the reachable states. Doesn't sound too bad at the moment, and check that they all satisfy this proposition. So let's do a concrete example. Let's go back to the traffic light controller example. So on the left is the extended state machine for the traffic controller, right? If you remember what it was just a very simple red, yellow, green light controller for traffic, and then you had a pedestrian input that could trigger the lights to stop the traffic. Now, what we're going to do is we're going to compose the system we're checking, wrong tool here, the system we're checking here, right, the traffic light controller, with a model of the environment, E. So this guy here is the system, this guy here is the environment. Notice the environment is providing the inputs to the system so that the overall composition M here, it has no outputs either, but it's a closed system. It has no inputs. That's what's important. Okay, it's a self-modelling system here. Okay, so typically, well, thinking about this, safety concern is we don't want the light to be green and pedestrian to be in the crossing state. Okay, they can't be walking across the road when the lights are green. We want that to hold globally, right? So that in every state that this proposition cannot be true. Once again, note that we can write it as a logical proposition, right? We can use our Boolean operators for that. Okay, so it is not green and crossing, not true. System and environment. Now, note that, right, we could model the environment differently, and maybe there are cases where we might model this differently. My ideal model for the pedestrian would be that it never wants to cross the road, so the lights are always green. Clearly, this is a more accurate model of a pedestrian who actually wants to wait and wants to cross. Actually, if I'm the pedestrian, there's normally no waiting, right? I'm just doing the crossing against the lights. Anyway, so the environmental model could change depending on the situation. Okay, so once again, those 2 dot points there. We now need to check that proposition globally, so we've got to scan through the reachable state space. We've got to enumerate them all first and then sort through them all. What we do is we use what's called a state graph to represent the system here. Okay? We'll see when we do some examples of that. Now, when our composed model M here is a finite state machine, so each of these composed models here that are put together have finite states, then any reachability analysis will terminate, in theory. Now, why do I say in theory? If they're both finite state machines, then surely you could scan through the entire state of spaces of the composed machine. Surely, right? There's a finite amount. It turns out, though, that things blow up very, very quickly. And the number of states can be prohibitively large, which would either consume too much runtime, so it's just sitting there searching the space for too long and you hit Control-C to interrupt it or switch the machine off or whatever, Control or Delete, or you run out of memory because searching a space, the memory that's required starts growing exponentially and you very quickly run out of memory. This is what's known as the curse of dimensionality, which is one of my favourite terms in embedded systems. Curse of dimensionality. And we get a glimpse of this because we know that when we compose models with their respective state spaces together, the overall composition has the cross of the two spaces of the states, right? So simplistically, if we have no overlap, right, we have 4 states and 4 states, the overall composition could at most have 16 states, right? We could remove unreachable states, but that's it. It gets worse though. If we have extended state machines where we have within particular states, we've got variables that tick up and count, it actually means the state space is much larger than, for instance, in this case, just 4. Because in the red state here, we actually are ticking a counter until we get to 60 and staying in the red state. So we actually technically have, I think, 61 states here. Count starts at 0 and gets to 60 before it leaves here. So it's stuttering, and it has 61 states there, technically. So dimensionality is a killer, particularly when you start using variables. Now, variables will help us, right? Variables normally reduce a big states machine down into something that's smaller, but we've got to remember that they still increase the state space, the size of the state space. Okay, we could use layers of abstraction to help, and it's quite a tricky balance here to have a state machine that we can start stripping things out and make it simpler in order to do reachability analysis, but maintaining what we need in order to model the system still. Okay, I'll give you an example of that for traffic light controller later on, where we can actually strip some of the extended part of it out. Okay, so now, the overall composition has something like 188 or 189 states because we have to account for values of count. An extended state machine just nicely hides that as a variable. Realistically, it's still part of the state space of the system. Now, but it does give us a nice compact representation here. Remember that because the pedestrian model here is non-deterministic, right? We don't know, well, some mechanism is going to generate a pedestrian wanting to wait, but we don't know what that mechanism is. We represent this non-deterministically between those two choices, that there is still a bit of non-determinism in the model here, right? We don't know if magically a pedestrian's going to just rock up or no one's going to rock up and the lights can go to yellow. Okay, so here's our nice compact representation. So how are we going to do reachability analysis? First way is via what's called graph traversal. So what I'm doing here is I've composed, I should go back a slide. I've composed the overall state machine. We don't normally do this. Particularly for large designs, we never do this. Why? For humans, if you're composing a few different machines together and immediately state space gets big, no one wants to look at an A4, A3, A2, A0 sheet of paper with this composition on there because it's just too tricky to follow, okay? It's good for small machines like this. I'll give you an example. One design I did many years ago had about 20 state machines doing different things. We had to do a reachability analysis on this for checking some safety propositions. We never actually did the combined composed machine because you just couldn't do it. Right? We never even bothered. What we did was we used a search technique. We'll talk about it in a minute. Okay, so there's a bit of a red herring showing you this, but it's useful for illustrating what a computer would do ordinarily. So what normally would happen would be we don't have that picture and a computer makes that state graph on the fly. It's actually developing as it goes. Okay, so the composed states as it goes. It starts, how does it do it? Easily, right? It starts with the initial state. You're always given the initial state of an FSM. You know what the next state or the update expression is, right, in order to get to the next states from that initial state, and therefore we can then start traversing that particular structure. So remember, our FSMs always have a next state relation or an update relation, and that's what gets us there. Now, if it's, so let's just say, we always have the next state or update equation. Yeah, we could call it an equation, mapping, whatever. And if it's deterministic, it means that the mapping is always to a single state. It's quite easy to do. So the mapping is to a single state. And if it's non-deterministic, the mapping is to a set of states. It's important to make this distinction, right? If it's a deterministic machine, it's easy. The mapping is only just, around the circle, if you like. But it's non-deterministic. We now possibly have multiple ways we can go. So there are two ways of doing it. There are depth or breadth ways of doing a search. And if you've done any computer science subjects, this might make a bit of sense to you. So anytime we've got a tree structure, if you think of branches and nodes, right, and leaves coming off them, we can either search down the most deepest path first, or go right down to the bottom of one of the paths and then backtrack. Or we could kind of go and look at each layer as we go down, breadth-wise. So we could go depth-wise down the search, or we could go breadth-wise. We'll cover both methods. Sometimes one is better than the other, and it's actually really tough to prove one over the other. It really depends on a particular case of a machine, and sometimes you use heuristics to work out which way is better. Okay, so here's the idea. So remember, we haven't built up a composition of the machines. State space has just exploded. It's too big. So we're going to do a search. So what happens is we use the graph here, S0, there's our first state, and we use the update function to work out where to go. So this state machine actually only has, the update function only provides us with another state S1. Okay, so it's a deterministic transition there. We could then use the update function to generate S2. Remember that we have, there's no external inputs into this system, right? The environment is embedded in the system, so we can explicitly know the transitions here. Then we might have, say, non-deterministic pathway here between two states. So at S2, the update function may generate a set of states now, and the set is only two, S3, S4, that's a set, and we would have to go and search those. So what we do is we maintain some set R, and we leave it open. Well, it's 0, it's an empty set to start off with, and we traverse downwards. So I should put that as the initial state there, right? And what do? Well, anytime we encounter a state, we just add it to the set of visited states. So S0, great, we add it to the set, R. We use the update function to get S1. We add it to the set of visited states. So there is an ordering here in my traversal. We do the update again, we get to S2. So we've visited S2 now. S2, that is a 2, and that's a comma. S2. Then we have a non-deterministic choice here. We've got a set of states. So we pick a traversal direction. We'll choose S3. So this would be our fourth choice. And we add that to the list of reachable yikes. We add that to the list of visited states. And notice that that state has no exiting transition. So we've essentially reached as far as we can get. There is no update function for that, state update. So we backtrack. So now we backtrack to here. We go back to S2 and we then examine the other branches that come off that in terms of transitions. So we would then hit S4. And when we hit S4, same again, yeah?
If there was a state below S3, would we go to that before backtracking back to...
Yep. So the rule is, you go down until you basically hit either a state that has no exit transition out of it or a state you've already encountered. Okay, so if this happened to be S0, well, we've reached a state that's already part of the set. We'll see that when I'll show you the algorithm. And yep, sure, we hit here, we backtrack here to S2. Well, we've already visited both paths. We backtrack to S1 to make sure that there's no way of visiting anything other than S2, and then we terminate, right? So we've terminated. So I've added S4, good, close the set. So that kind of works, right? It's a nice set procedure, traverse down, hit the bottom, move up, keep going back down any other pathways you didn't take. It's kind of like a maze escape algorithm almost, right? Where you just turn left every time, and when you hit a wall, then you start going back and taking right turns. How this is implemented in hardware, or software actually, but we implement a stack. Okay, so we're basically keeping track of the states that we've encountered. Why is this important? Well, if we're looking for in that tree structure there, say S, some state that we don't want to be in because it violates our LTL proposition, right? So if P doesn't hold in one state S, then GP doesn't hold. Therefore, we have a violation of something. So what do we need to do? Well, we need to keep track. Firstly, we need to know if we ever end up in S, where S is a bad state. And secondly, then, we would want to know the trace of how we got there, right? There's no point in basically putting in some monster composed machine into a simulator and say, do I ever get in state S? And it comes out, it says yes. Okay, that's not going to help, right? We need to see the trace of actually how we've got there because we need to modify things, right? Fix it, basically. So how do we do that? We use a stack. So every time we go down a path, we put that state on a stack, and every time we go back up, traverse back up again, we remove it from the stack. So if we remember what a stack is like it's just a temporal structure basically that maintains the order of things that you've seen. Anytime you see a state, you chuck it on the stack. Anytime you traverse back up it, you pull it off again. So the stack, show you a picture of it, the stack would look something like this. If we're traversing down just a simple path like this and we hit bad state S, like an error state that we should never get into, what we're doing is we are progressively filling the stack. We're growing the stack vertically here. Remember, a stack starts at the bottom. So we encountered S0, S1. We've hit S. Then we can just simply read the trace from the stack. We could read it backwards if you like to work out the way how we got there, or you could read it forwards from S0. Doesn't matter, but you can read it. The ordering. As I said, anytime you go down branches and then work your way back, you are popping them off the stack, right? So you're only keeping track of the current pathway that you're down. All right, so stack is a nice way of doing it. But once again, this is problematic. Firstly, computation time. If we've got a lot of paths to follow, that's bad. But now we need a memory structure to keep track of these paths. So if the path gets very deep, this stack could grow very, very big and we run out of space, right? Memory space. So there's the memory issue, and then there's a computation time depending on how deep these things go. All right, so let's do the example with the traffic light controller. We're going to do this depth-first search. Once again, this is the composed machine M that has the environment composed in with it. We don't normally have this available, right? A computer would be able to take the machines and work through them, right, without composing them. But we're going to do this because it allows us as dumb humans to be able to visualise this. So in the initial state, here is the composed state of Reddit crossing. And so that's our S0, if you like, right? The reachable set that we've visited. Now, if you can imagine, remember, an extended state machine abstracts the fact that there are actually 61 states in that red crossing state because there's a counter that has to maintain state, right? Counter has memory, keeps state. So if you are in red crossing 0, you can almost sort of see all these other possible states as well, right? Well, no, actually you can't. You can only see one at a time. You just see red crossing 1. There's only one transition there, okay? Because this little counter is increasing on every reaction, right? The default transition here, right? So counter's ticking, tick, tick, tick. You are just ticking, 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 all the way up to 60. So there's no decision to be made there. It's just a straight line every time you're ticking. So there are 61 states there already. Okay, so finally we get to 60, and then we have an alternate pathway. Well, there's only one, and we follow that, and we then hit the green none 0. Yes, because we reset the counter here in the extended state machine. Once we hit 60, we reset it, so it's back to 0. Now, what happens here? So we've got this default transition here. Once again, you can think of the state space as being blown up in that state as well, that we have the increasing counter, tick, 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 up to 60. But this is a non-deterministic transition here, right? That, remember, this was composed from just a pedestrian just rocking up, and we don't know how that mechanism happens, but it can happen, right? So at some point, for count being less than 60, we can still even go into this state here, yeah? Or we can just be remaining in this state. So what we've done is we've actually taken the non-deterministic pathway this way first. Now we could also see that we've got a space where we can go down this pathway, and we've got the yellow weighting 0 because we've reset the count to 0 again, state, and that ticks up to 5. So we've got another 6 odd states, something like that, there as well. Huh. Lastly, we have to look at what happened if we took that path, so we backtrack again, right? So we got, I should explain this better, I'm not a very good computer in terms of explaining stuff. So once we've got through to here and we've ticked through all the possible states here, right, we know that that transition takes us back to a state that we've already visited. So we terminate that branch and we go back and then we go down this branch. Okay? Imagine grabbing this and trying to turn it into that graph, right? A top-down graph. So we get back to where we were, we backtrack to here, then we take this part of the non-deterministic branch, okay? And that's the pending waiting state. We get to 60, then once again, we get back to the 0 yellow weighting, and that's already part of what we've searched. So we have built up the correct set of states. Oh. Right, so that is tedious. Now, it's been exemplified by using the composed model, which we don't do in practice, okay? Because composing it is just bad in terms of computation. Now, once we have a list here of all the reachable states, then we can simply just then check that if this proposition holds for all of these states, then we can say it holds globally, and therefore what we want to happen has happened, or not happened. In this case, green and crossing. So here we have no joint state here where green and crossing, the machines are in the green and crossing states at the same time. So we can conclude safely that the machine never allows the pedestrians to cross while the cars are also going. Now, once again, as I said, once you have this extended state machine, composed state, it's obvious, you can see. But remember that a computer, when it's doing this algorithmically, will just be using the two machines like that, right? It won't actually formally compose them together. It will just deal with them independently. And from this diagram here, it's, to us as humans, not obvious that green and crossing are both in the states at the same time. Okay, so that's depth first. So you're kind of traversing down the pathway. Anytime you hit a dead end or you end up at a state you've been to, go back up the pathway and take another branch if there was a choice. It turns out that the depth first, sometimes it's good, but most of the time it's bad. Okay, the state just blows up, so you've got a massive search space to go over. So there's another way of doing this, and it's using the symbolic approach. This is known as breadth first. So it's kind of looking across ways instead of going down individual branches. Right, how so? What we're going to do is we're going to use the power of Boolean algebra in a way that computers can calculate things on sets much better than on individual states. Okay, so you're using power of logic, if you like. Right, so we're going to use Boolean algebra, and this is how we're going to do it. We're going to have the set of states of the machine, some finite set of the subsets of the amount of states of the machine. We're going to have a function that maps the states to either 0 or 1, right? True or false, if you like. In this case, where for a given state that's in that subset of states, it comes out as 1. So it's a checker. That's all it is. It's just a checker. You've got some magic function. It's so magic we're not even going to describe it, right? FC. It can check whether or not X is in the set, and it tells you if it is or not. Okay, now that's very useful, right? Because if we have a set of states and we've got another state and we want to check if it's in that set of states, and we can do that easily, then we don't need to do this backtracking, searching on particular states. We can do it on sets instead. Okay? Right, so a simple example. I might give a simple example. I'll talk about the state transition function first. Remember that we're always going to have some mapping of this, given a state, where to go next. And that's the state transition function. Okay? We call that delta, and given a state, it yields either a single next state if it's just a deterministic machine, or a set of states if it's non-deterministic. Remember, once again, there's no input to this machine, so we can't have deterministic multiple branches. Doesn't make sense. They've got to be non-deterministic. All right, so each S, for each state, you can have a Boolean function that represents this next state operation, the update operation. And even better, we typically enumerate states, well, computers have to enumerate states as binary. Okay, so you're restricted to ones and zeros. So, for instance, let's do it this way. So, let's say, looks like a face, doesn't it? Double zero state. Let's say your state machine had 4 states, potentially 4 states in it, and maybe it was just only had 3 states. So that's, if big S could be 4 states and C is 3. It's a subset of states. If you're in this state here, we could call this S0 if you like, the starting state here. We're looking at the function, the state transition function here is a mapping, and it's a very simple mapping. It's a mapping to either here or to here. So the update function, right, well, when it's acting on S0, it's quite restrictive. It only has a domain of that because it can only operate on that, and it has a range of only 2 values. So because these things, the states are realistically encoded in binary somehow, just ones and zeros, and even non-deterministic mappings like this are just expanding the range of it, right? It turns out that the state transition function yields quite simple Boolean algebra, right, to generate those possible next states. And this is all to it. So I'll show you a picture of how this kind of evolves over time. So where this starts is in Q0. So imagine you're in S0, you're in the initial state, and Q0 is the set of states that can be reached from S0. So for instance here, it will just be 1, 0, 0, 1. That's a set, 2 elements in the set, big deal. And what you're doing here is you are doing it breadth-wise. So this is a pretty poor example because depth and breadth are almost equivalent here. So if we had additional states down branches this way, right? That's where it might be a bit different here. So Q0, right, the set of reachable states from the initial state here, well, we're mapping to a set here. Then here there's no mapping, but here there's a mapping just to one other state, and then here there's a mapping to another 2 states. So you can kind of imagine that if we're successively applying this update function, we're increasing the set space of reachable states that we've seen. And I'm not going to explain how this is done because this is an implementation issue, but if we have a nice way of checking whether or not the state is contained within a particular set, then we can just flag that it's true, okay? Remember, the idea here is we're checking for a bad state S, for instance, like the traffic light controller allowing people to cross when it's green. So all we have to do is check if S is reachable. So as we are evolving the set of reachable states, and we've got a very efficient search tool, we're given a particular proposition for a state, we can search that space really quickly, and we can, then it turns out to be fairly efficient. So we can then also follow the path back and get a trace back to how we got to that state as well. We won't go into the details of this because there are a few different ways of doing it, which are beyond the scope of the course. It's more computer science-y sort of stuff. But here is the basic algorithm as I just described. And it's almost, you know, it's easy to describe this in words. To formalise it, it kind of looks a bit confusing, but it's quite simple, right? So, so you've got you start off with a reachable set of the states. Is just S0, your initial state. Set R new equal to that. While R new is not empty, then what you do is you basically are looking for the state S prime that's generated by using the update function. So once again, it's looking across ways at all for a given state of all the possible states you can get to. Okay, from that. Instead of traversing one down path, you're looking across. If the 3 arrows coming out, you've got those 3 states are now going to be added to your reachable state set. Okay, so this is all this is essentially saying here. There exists some S in the reachable set such that the updated transition or whatever is mapped. Say that again. You map the particular state by the update, you take all those particular states and you then chuck them in this new state, a new set. But what you do is you exclude any states you've already seen. So that's what this /r is doing here, right? So you can imagine, we could imagine maybe a single S0, say 3 states coming off there, and then maybe you could have a loop back to a state that you've already seen. So you want to exclude that. So this search continues. You exclude R, then what you do is you find the union of them. Okay, so you're finding new reachable states as a set, and you're unionising them, if you like, with what you already have. You store that. You then, it's not the empty set. You try and find new states. You union them again. Eventually, you're going to run out of new states because the generation here is going to generate just R, right? Everything in R. So when you exclude R, it's an empty set. You've found everything. Okay? So this basically eliminates what's already been seen, this little part here. All right. So you can actually download programs that can do this. There are free tools that can do this for a given FSM. If you program the FSM, it can do a symbolic search for you, a breadth first search. Remember, the idea is that we are checking if we end up in one particular state here. Once again, it is still somewhat cumbersome over a large state space to be doing this sort of search, and we can eliminate the complexity a little bit by using abstraction. So I think I'll have to leave that there, but what we'll do is I'm going to run through that little algorithm in the next lecture on this system, remembering once again that having this composed model is not quite right. We will do it just by looking at the individual states of the machines. Okay, we'll leave it there for today. All right, we'll get back into this and we'll look at abstraction next lecture to reduce the complexity of the state space.